Now, next on my list, I want to talk about what I refer to as indeterminate forms. So, take a peek at this limit. Check out what would happen if both this numerator and this denominator involve outputs of functions that are increasing without bound. I refer to that as an indeterminate form. It's indeterminate because I really don't know in the end, as a general rule, which one of these functions is going to beat the other one out. For example, if this numerator increases that bound much more rapidly than the denominator increases that bound, this whole thing's going to go to infinity. If this thing downstairs increases that bound much more rapidly than the numerator increases with that bound, that whole fraction is going to go to 0. So maybe something in between might even happen. It's a battle, it's a race of which one's doing its behavior fastest. And so for me to evaluate such a limit, we've had some tools at the beginning of the semester, but they're very limited. So let me give you a much better tool. It's so important, it's got a name. Please forgive me, please forgive me. I know the French don't possess like that. So given that I have a limit in this indeterminate form or equivalently this indeterminate form, what I can do is the following, and I'm going to present this without verification, without proof. I'm leaving that for you since this is an independent learning course. But you will find your book, at least a portion of it. Divide that limit. I might want to divide this limit instead. Or instead of looking at outputs, how they change, I'll look at how the rates of change change. And as long as I'm one of these two indeterminate forms and I have continuity and well-behaved functions, then I certainly replace this limit with this one, and oftentimes it helps in evaluating the limits. Now, my first example is probably a waste of time because you and I know full well that we can multiply top and bottom by 1 over n squared, and we're able to divide the limit. Or we could rely on pre-calculus, talk about a corresponding continuous function. My goodness, I don't have x's in here. It'll be a rational function. We know we have a horizontal asymptote, but y equals 5/2. So maybe my first example is a waste of time, but let's just give it a shot anyways. I said 5/2, I think I meant 2/5. Because it's an infinity over infinity situation, I can apply L'Hopital's rule. And again, I know I have other techniques for actually evaluating this integral, but I said integral. I know I have other techniques for evaluating this limit, but using L'Hopital's rule one more time. And now, excuse me, that limit evaluates to 2/5. Please excuse me. Notice I don't have the LIM out front. I don't need to because the limit of a constant, as x does anything a Darwin pleases, is just a constant. Now, if you don't mind, because I'm the one grading your work, could you tell me when you've applied L'Hopital's rule? I typically put a circle around the equal sign. Some people put an L above the equal sign instead of a circle. Some people put an H. Some people put an LH. I don't care what notation you're using. Just show me, communicate to me that you applied L'Hopital's rule. Now, we already know this limit, but to evaluate this limit, I took quite a bit of a time, I think, with a big geometric argument with the squeeze theorem to prove to you that that limit evaluates to +1. That's because back then I did not have L'Hopital's rule in my back pocket. Now that I do, I can apply L'Hopital's rule to evaluate this much, much more easily. The derivative at the top is here. The derivative at the bottom is here. But as x goes to 0, that numerator goes to 1. So the whole fraction goes to 1. Piece of cake. Here's another infinity over infinity situation. By the way, I should have said that in my last example. That is indeed a 0 over 0 situation. So I did have the mathematical legal right to apply L'Hopital's rule. I should have said that. Here I got an infinity over infinity situation. I don't see any other way around it, so I'll apply L'Hopital's rule. Looks to me like I can apply L'Hopital's rule maybe 5 times. Oh, I can't write it. Now applying L'Hopital's rule one more time. So I want you to carefully take a peek at what I just did. Because what I think I've just done is I've committed a grave mathematical sin. Because technically speaking, that was not a legal application of L'Hopital's rule. Because technically speaking, the previous limit was not an infinity over infinity situation. It was a constant over an infinity situation. So L'Hopital's rule does not apply. I have to admit, at this stage of the game, when I'm taking the limit of the ratio of a constant to something that's increased, not down, that limit does indeed evaluate to 0. I did have the right answer. I just didn't have the correct answer for the correct reason. Okay, so I fixed that clumsy mistake. Now that's legal.